Apache Kafka serves as the primary infrastructure layer for routing and processing millions of real-time events per second. To understand the adjustments required to sustain these loads, we worked with the engineering team at Royal Research to deconstruct the system's internal physics. This environment consists of producers that ingest data, brokers that manage storage, partitions that enable parallel processing, and consumers that pull the final data feeds. While default configurations are stable for standard workloads, high-volume environments require active intervention to bypass the limitations of the default settings. Tuning is governed by a fundamental physical constraint. Prioritizing one performance metric inevitably forces a degradation in another. This relationship is often visualized as an iron triangle, where throughput, latency, and scalability compete for the same system resources. Increasing the rate of data ingestion creates a direct cost in delivery speed. In a high-throughput scenario, you are essentially trading time for volume. Optimizing for these variables requires isolating configurations across the producer, the broker, and the consumer. Since no single setting satisfies every use case, engineers must define a specific frontier of trade-offs aligning with their data's urgency and durability requirements. We begin at the producer layer, where data first enters the cluster. By increasing the batch.size parameter, we group individual events into larger blocks. This reduces the total number of network requests, allowing the system to process more data with less overhead. This batching logic is paired with linger.ms, a parameter that acts as a release timer for these data containers. The linger.ms setting forces the producer to wait for a set duration to allow the batch to fill. If the timer hits 0 before the batch is full, the data is sent anyway, a delay that improves throughput at the expense of immediate delivery. To further maximize network efficiency, we can apply compression codecs like Snappy or gzip to shrink the payload size. This reduces the volume of data moving across the wire, though it shifts the burden to the CPU, which must now handle the encryption and decryption cycles. Beyond volume, we must configure the acknowledgement settings, or acks, which dictate how many replicas must confirm receipt. Setting acks equals all ensures the highest level of durability, but it forces the producer to wait for every in-sync replica to respond, adding a significant latency penalty to every write. At this ingress stage, achieving maximum throughput necessitates a calculated increase in the time it takes for any single message to be confirmed. Once data leaves the producer, it reaches the broker, the system's storage and coordination core. Kafka operates by appending messages to a sequential commit log on disk. Because every piece of data must be physically written before it is considered sent, the broker's performance ceiling is defined entirely by the speed of its disk I/O. To bypass the mechanical bottlenecks of spinning disks, high-volume clusters rely on SSDs and spread log segments across multiple physical drives to parallelize the write load. We solve storage congestion logically through partitions. These act as the primary units of parallelism, allowing a single topic to be split across multiple brokers simultaneously. Increasing the partition count horizontally distributes the processing load. As we add more lanes, the volume of data handled by any single broker decreases. However, this requires a consistent hashing strategy for partition keys. Without even distribution, one partition will bulge with excess data, creating a bottleneck while other brokers remain underutilized. We can also adjust the log.segment.size. Larger segments reduce the frequency of disk flushes, which improves throughput but increases the amount of memory required to keep those segments open. Managing the broker layer is a task of aligning physical hardware capabilities with disciplined logical routing. The final stage of the architecture is the consumer, where data is extracted for processing. The primary lever for consumer speed is the fetch.size parameter. This controls the volume of data pulled in a single request. By increasing the fetch size, the consumer retrieves larger blocks of messages, reducing the frequency of network calls. Beyond retrieval speed, the system must maintain rapid detection for consumer failures to prevent data from backing up. This is controlled via the session.timeout parameter. A shorter timeout allows the cluster to quickly identify when a consumer has stalled or disconnected from the group. When a timeout occurs, it triggers a rebalance. The partitions assigned to the failed node are instantly rerouted to healthy members of the group, ensuring that processing continues without manual intervention. Consumer tuning is a balance between maximizing the volume of each pull and maintaining a responsive safety net for hardware failures. In a production environment, these individual components function as a single interconnected system, Configurations are only effective if they are supported by real-time observability. Tools like Prometheus and Grafana are used to monitor JMX metrics, providing visibility into CPU cycles, memory pressure, and disk saturation. High-volume pipelines must undergo extreme simulation testing to identify the exact point where the current configuration fails under stress. When those critical thresholds are reached, auto-scaling policies can dynamically provision new brokers to absorb the increased load. We must also account for the performance impact of security, often referred to as the security tax. Enabling SSL encryption and SASL authentication provides necessary protection for data, but it introduces a computational overhead that reduces the maximum possible throughput of the cluster. Finally, consistent operational maintenance, such as log compaction, is necessary to prevent the accumulation of obsolete data from slowing down disk operations. Maintaining a high-performance Kafka cluster requires a continuous loop of monitoring and adjustment to balance the competing demands of speed, reliability, and scale.